So hi guys, I'm Bartek. I'm a front-end developer at NetGuru. Here's my Twitter handle and my website if you would like to contact with me afterwards. And yeah, today we'll talk a little bit about internet. Probably most of you pretty much know how to make requests, for example, with Fetch API in browser, for example. But do you know what actually happens under the hood? So what is going on when we, for example, enter a web page and press enter? So I hope to clear this up a little bit. So here we have got two computers. And yeah, so the internet is an network of computers all around the world. So to have internet working, we have to have two computers connected. So what is the way to connect two computers, for example? So we can use fiber optics, we can use Wi-Fi, or we can use simple old normal copper wire. And this is what is still used in Ethernet cables. And this is where we'll start. So you can imagine we have data in computers. So those are usually ones and zeros, so bits. And we would like to send them from one computer to the other. So how can we actually do it? Using a simple copper wire. So using a wire, we can send electricity. So we can have a waveform. So it is a waveform of voltage inside the cable. So yeah, we can express data going through the cable as zeros when we have no voltage, and 1 when we have some kind of voltage. Let's say 1 volt. So yeah, sounds reasonable to do it like this. But yeah, it's not that easy. So the problem is that we have to know where to actually read the data. So at the top we still have the same waveform, and at the bottom we have a clock of a computer. As you have, we have this form, and when we go up, we read the data. So here we've got 0, 1, 0, and so on and so forth. And yeah, it still looks okay, but the problem comes when we have a computer that has a little bit different timing in its clock, and it is really common because no computer is perfect. So yeah, as you can see here, we've got another clock that runs a little bit slower than the previous one. So yeah, we read 0 here, 1, 0, but you can see that is almost wrong. And we have another one, but here we should have 0. We should have another one, but we have 0 because the clock stretch a little bit. And it is called a bit slip. And yeah, so there is a way to mitigate it. So some clever guys came up with a solution that maybe we should incorporate both of those things into one stream of data. So instead of saying that 1 is a high voltage and 0 is a low voltage, we change it so that the 0 is the change from high to low, and 1 is the change from low to high. And it goes again and again. And you can see this red dotted line in here. It looks a bit like there's some magic, but there really isn't. Yeah, and it is called the Manchester code because people in Manchester came up with it. So yeah. So here you can see how it can work with the dotted line. So here is another chart of a voltage measured on an oscilloscope. So an oscilloscope is a device that can measure voltage and graph it in a real time. I don't have an oscilloscope myself, so I couldn't bring it here, but you can have a screenshot. So yeah, one of those gaps is at 100 nanoseconds, and as you can see at the bottom. So 100 nanoseconds is a 1/10 millionth of a second, so it goes quite rapidly. So yeah, recap: 0 is from top to bottom, 1 is from bottom to top, and yeah, we measure the voltage every 100 nanoseconds. So you can see here we're going down. Nope, here we're going up. So it's 1, and again we go up. So it's the same situation with the dotted line. So you can see that in the span of 100 nanoseconds we were able to go back down again and back up again. So it wasn't really a problem. So yeah, we go 1, 1, 1. Yeah, I should enter. Yeah, so we can now send bits, but in computers we usually like bytes. I don't know, you have megabytes, gigabytes, but that's just a name. So yeah, so if we have string of bits, we can divide them into bytes, and for example get in some kind of characters. So we can divide it like this, and we have H, E, L, and probably there's something going on there, so it says hello. But what actually prevents us to do it like this? It's the same string of bits, but arranged in a little bit different way, and it gives us garbage. So it is a problem. How do we do it? There's another interesting thing called the Ethernet packet. Ethernet, yeah, frame, sorry. And yeah, it looks like this. This is like a written form of it. So, and again, at the bottom we have again the oscilloscope reading. So at the beginning here you can see that we have a straight line. So it's like a time of silence to give the other computer time to get to know, okay, so there's no data being sent right now, so we're waiting for data. And then we have this string of ones and zeros, which are alternating, so it's 1 0 1 0 for 56 bits. It is called here. It is called the preamble, and you can see here that is 7 octets. An octet is basically a byte. I don't know why it's called like this, but it is. And you can see we have 1 0 1 0 1 0, and here we've got a frame delimiter. So we still have 1 0 1 0, but at the very end we have 2 1s. So when there are 2 1s, we say, okay, after the second one we start the data, and from now on every 8 bits are basically a bytes. So yeah, and the blue one is the data. So data starts in here, and we've got the data sent. So we've got a MAC addresses, ether type that it really isn't used right now. Payload, so payload is actually the data that we want to send, the actual data. And the frame check sequence, so it's basically data that confirms the main data is correct. And at the end, we've got inter-packet gap, so it's pretty much like this. And it says, okay, the packet ended here. You should wait for the start of the other one. So yeah, so it's the same thing, but you can see that in here we've got MAC addresses. But when you think computers and maybe more of networking and internet, you use IPs instead of MAC addresses. And there's a simple explanation for this. So let's say we have a network like this, and we want to send some data from A to B. All of those are intermediate computers. So if you wanted to send the data from A to B, we would have to know the MAC address of this computer, and probably this and this and this, because we have to know all the path that it has to have, because we can send from one to the other MAC address, and there's nothing really magical in between. So that's why the IP was introduced. So IP is an internet protocol. And we have IP addresses. I hope that all of you know them, like how do they look. And the very important thing about them is that they are routable, contrary to MAC addresses. So MAC addresses are just random numbers assigned to each network device, but IP addresses have actual meaning in them because they can be structured. So you can see if dots here, here, and here, and they somehow divide the IP address. So when we want to send the data from A to B, we send the data to this computer because we know like it's a gateway to the world, and we just say, okay, I want to send it to this one, and you handle it. So each computer has something called a root table. And yeah, we've got IP addresses, and you can see those numbers at the end. So these numbers at the end are masks for the IP addresses. So it says just read 16 first bytes, and it tries to match this IP address. That IP address. So the destination IP address the best as it can. So you can see 192 is at the start of those two, but the best fit would be this one. So it says, okay, so go to 10.4.5.4 through the network device number 2. So it would go here and there, and at the end, it knows that the this computer has this IP address, so it's oh, it's not here. Never mind. But it should directly route to this computer. And yeah, more letters. So it is a packet of the IP. So it's still more data at the beginning before we send the actual data we want to. So we've got something like version, IHL, and all of those things that aren't really that important, except for the thing that I didn't write here. So we should have IP address and IP address here and here. And yeah, it says, okay, so from IP address here to that one. And all of this lives in this payload section of the Ethernet packet. So it basically looks something like this. So we have the Ethernet frame. So we've got something at the beginning. So it's this preamble thing. And at the end, we've got the gap between packets. And the IP packet that has some stuff at the beginning that says where should we go. And the actual data that is being sent. Yeah, I think it's duplicated. Yeah, so as there should be IP addresses, you can see that we are sending data to the IP addresses. But actually, when you type the URL into the web page, you don't usually type IP addresses like now. So we have, we've got domains, so WarsawJS.com, and it does some magic to work it out, and this magic is called DNS. And so suppose we've got a user, we've got a domain, and they want to get to know what this domain points to which IP address this domain points to. So it says, okay, I should connect to the other server that is called the DNS resolver. And it is usually your ISP, so Internet Service Provider. So in Poland, it would be something like UPC, so the company that provides you internet. But you can change it in settings of your computer. And it says, okay, so where does WarsawJS.com points to? And it can have some cache of its own. And if it knows right away, it sends it back. But suppose it doesn't know. And so it says, okay, I'm going to ask at root. And you can see that here that I have put the dot at the very end. So actually, this is the whole host name or a domain name, that this is a root, so the very end of a, let's say, chain that the domain can have. So the DNS resolver says, okay, so I'm going to ask another server that is called the root server. So there are 13, let's say, versions of them all around the world, and they are like a single source of truth for everything, so they know where to ask later. So okay, so we asked here, okay, so what should I do next? I know that the domain is .com, so it says, okay, so the .com domain is handled by somebody else, and it says to whom they should call now. So then they go to the TLD server. So TLD is top level domain. So it's basically the thing that is in the end. So it could be .com, .net, .org, but also .pl. And it says, well, you know, I know I am the .com, so WarsawJS is handled by yet another server. So it says, okay, it's another server, you handle it. So it says, okay, I'm going to handle it. And it asks the authoritative server, so it's the server at the very end that handles all of these domain. And it says, okay, so the actual server that hosts this web page is some kind of an IP, and that's the one we were looking for. So it goes back to the user, and then user can make a request directly to the server that we want to know. So basically we know the IP address of the server that stands behind the domain. Yeah. So we've got that covered. So now we should connect actually to the server that we want to. So we use something called TCP. So TCP is Transmission Control Protocol, and it's yet another protocol that allows us to basically send the data in a few ways. Maybe not in a few ways, but the way it is sent could be described by a few words. So for example, we can say that the connection is reliable. So you can recall that we had something called checksum in the Ethernet frame, but it just checks whether the data was correct or not. But TCP also provides us the thing that if the data wasn't correct, the server will resend the data that wasn't correct. And as well, it allows us to do really important thing, at least right now. So sending more data that is allowed inside a Ethernet packet. So it was, I think, something like 1400 up to 1500 bytes, but it's like for really high-speed links between countries or even continents. So yeah, so we have a TCP. And the important thing about TCP is that it has connections in it. So at the beginning of talking, it's a little bit like talking through a phone. So you call to somebody, so you input their phone number, so it's our IP address. And then you pick up the phone and say hello, and the other side says hello. And then you can start talking, at least if you're polite. And at the end, both parties say, okay, bye-bye, okay, bye-bye. And then they hang up. So that's the end of their connection. And TCP does something similar. So suppose we've got a client and we've got a server. So those names are actually like client and server are not really strict in the sense that once we connect, both devices are just computers, so both can send the data and both can receive the data. So we usually say the client is the party that starts the connection, and the server is the one that is being connected to. So we start our communication. So client sends a packet with a bit in parts of where there are flags. It sets the bit for syn, so synchronization. So it says basically, okay, server, I'm gonna start sending the data from number 0. Actually, it's never 0. It's usually a random number, but for sake of easiness of looking at it, I said it's a 0, and also if you use some network software to track the data that's coming through, will also usually set this one to 0. So server says ACK, so acknowledge. So okay, I'm gonna start to. I'm waiting for the first segment in sequence, and also I'm gonna send the data from 0 as well. And the client says, cool. I'm gonna wait for 1, and here we have the actual connection established, and this is called a three-way TCP handshake. So that's just the beginning of a conversation, and then we can send the data. So we send let's say we send 20 bytes of data, and we send okay. That's the first one, and the client says, cool. I'm waiting for the 23rd one, and now we're hanging up. So server says bye bye. So it sends the fin command and says, okay, it's the 23rd. And it's the client says cool. Server says again. Now the client says bye bye. Server says cool, and that's it. So the end thing, so the ending of the connection doesn't have to happen right away. So we can have multiple like lines of sending the data and then saying it's okay, I got all of the data. So that is also basically what HTTP does. So it doesn't close the connection. You can send multiple requests through one TCP connection. And yeah, so this is a screenshot from Wireshark. Wireshark is as I mentioned, a software that allows you to basically sniff all the data that comes through and from your computer. And you can basically see in real life how all of those things went through. So we, first of all, we have a handshake. So syn, ACK, and ACK. Then we have a request. So the request goes through. And there's response. So you can see that all of those were just on a one TCP connection, as we had just one handshake, and at the end we have the end. So we hang up. So yeah, this is again how it looks like. So we've got an Ethernet frame. Inside an Ethernet frame we have an IP packet, and inside an IP packet we have TCP segment. And that is actually called an encapsulation. So we have all the time we're building the data inside one frame, and then inside this frame we have another frame, and inside this packet we have another segment. So we can have it really modular to how we structure the data sent through the internet, and because of that we have so many standards to use. So yeah, we covered TCP, and quickly I'm gonna talk a little bit about HTTP. So I imagine that most of you pretty much know HTTP, but this is a raw request to the HTTP server. So at the top we've got something called the request line. So it is a line that has three parameters. The first one is method. So we can have a get method, post method, put method, and a few other. And we can specify it in here. at the beginning there was also only a GET request, but well, as the internet grew, they had to add something. Then we have a URL that we want to make the request to. At the end, there's an HTTP version, so nothing really spectacular. Yeah, and you can see here that we are not using bytes right now, so we're using actually characters. So you see that those are structured into lines, and they are actually lines, because each of those lines have to end in 2 characters. That it's usually called CR and LF, so it's \r\n, and those 2 are actually used because CR is an abbreviation of a command that was used a long time ago, and it was called a carried return. So at the beginning, when you printed the data from the computer, you didn't have a terminal that you would put the data to, but it was actually written on the piece of paper. It was printed. So it says, okay, carried return, so bring back the thing that printed back to the left. And then you had LF, so line feed, so push the paper to the top so I can write onto a new line and not scramble the other data. And then we have headers, so these are also still lines. So each of those ends in CRLF. And before the colon, we've got hosts, so name of a header, and then we've got a value of a header. And yeah, and quite probably not many of you know that you can actually have multi-line headers. So to have a multi-line header, you simply put a tab or I think spaces, I'm not sure, on this, and you can have a multi-line header. And at the end, we've got body of the header. So the length of this body actually is in here is set here at the end. So content length. It says that it has 35 bytes, but it doesn't always have to be there. There are a few other ways to handle the length of the body, but I won't go into it because there are many of them, and depends on the implementation. And yeah, and here we have a response. So pretty similar. We've got a response line, so version, the status code, and the status name. You can actually, in most cases, write here whatever you want. Then we have headers and the body. And yeah, so we covered the internet. So thank you very much.
Short question session. Are there any questions? Yes, of course.
When you spoke about DNS, you said that there are, I believe, 13 root servers. So how come does it scale?
So I said that there are 13 versions of them, and actually there are around a little bit more than 1,000 of those copies all around the world. So there are 13 servers which are taken care of by 12 companies. And yeah, they just copy all of the data and send it quite often to update all that.
But when my computer makes a request to my ISP, how come this ISP knows the exact IP address of the server?
So there are, those are the top ones, so you cannot just guess them. So each ISP has to know exactly what IPs do they have. So it's written down, and they have to know.
It's hard-coded. Okay.
Yep.
Thank you.
Exactly.
Thank you, Kasper, for this clever question. Any other questions? One question.
I would like to ask about HTTP requests because I know that there are GET and POST requests, and where do these feed? I mean, how does the computers distinguish is it a POST or GET request? Is it hard-coded? In which part of the HTTP?
So right here, so we've got a request line. So at the very beginning, you basically say which method you would like to. You can technically you could put this here anything, but it's up to the server to understand that you want post, put, or delete, or get.
Okay, thanks. And one last question, maybe someone. I have a question.
Yep.
You said the voltage difference makes the bit. How about optic fibers?
Okay, so that's completely different methods of doing so, and I actually don't know how it works. So that's my question.
Thanks for your honesty. Okay, thanks very much, Bartek.